Welcome to qnawire.
For letter A, we need to solve for the velocity of the mass center, let's say that's point G, of the panel after the bullet is embedded on it. So, we're looking for VG. So, I have here a sketch of the problem. So, a bullet with a mass MB, which is 45 grams, is fired with a velocity VO into a 9 kilogram panel, square panel that is initially at rest. So the impact caused an impulsive reaction with force F at point A, and also upon impact, so that's in the second part of the sketch. Now for the third part, upon impact, the panel rotates with angular velocity omega about point A. The mass center, which we assigned here as point G, now moves at a velocity vg. So that's basically the setup in the problem. So before we start writing the equations, so let's first make some conversions and initial calculation of the quantities. So converting the mass of the bullet to kilograms and the dimensions in millimeter to meters, so we'll have, so mass of the bullet equals 45 grams times the conversion factor, so 1 kilogram is 10 raised to 3 grams. So this is equal to 0.045 kilogram. And then for the side of the square panel, which is B, so B is 200 millimeters, times the conversion factor, 1 millimeter is 10 raised to negative 3 meter. So cancel millimeters, so we'll have 0.200 meter. And lastly, for the H in the diagram, so the distance from point A, where the bullet hits the panel, is 150 millimeters. So multiplying it by the conversion factor, 1 millimeter is to 10 raised to negative 3 meter. So this will be 0.150 meter. And then for the moment of inertia, so based on the shape of the panel, so the moment of inertia is given by 1/6 the mass, so the mass of the panel times the length of the side squared, which is B. So this will be, so 1/6 times the mass of the panel, which is 9 kilograms. And then the side B, length of the side B, so 200 meter square. So the moment of inertia, I, is equal to 0.06 kilogram meters squared. So those are the values that we have. Now, since Vg here is linear velocity, so it can be expressed in terms of r and omega. So we can actually get an equation from here. So Vg would be equal to, so G here is at the center, so that would be half of the side. Its distance from A would be half of the length of each side. So that would be B over 2 times omega. And as we know, B is 0.200 meter. Divide by 2, so that would be 0.100 omega. So this is our equation 1. Now, we'll write the equation for moments about point A. So, taking the counterclockwise direction as positive. Now, for simpler analysis, we will assume that the mass of the bullet can be neglected upon impact. So, our equation would be, since our velocity here the velocity of the bullet before impact is directed at 30 degrees from the horizontal. So our equation would be, so mass of the bullet times VO cosine 30 degrees. And then of course the point of impact is at a distance h from A. So times h. Then plus the mass of the bullet, VO sine 30 degrees times B over 2 plus 0. So equals moment of inertia times omega plus mass of the panel times velocity g. Then g is at the center, so that's B over 2. So we can combine some terms here to make it simpler. So we could write this as MB VO times H cosine 30 degrees plus B over 2 sine 30 degrees equals, so same left hand side, I omega 2 plus mass of the panel VG B over 2. So this is now our equation 2. So substituting the values that we have and also equation 1, which gives the value of an equation for VG, so this will become, so 0.045 times the VO, which is 400, then 0.150 cosine 30 degrees plus 0.100 sine 30 degrees equals the moment of inertia, which is 0.06 omega plus the mass of the panel, which is 9 times our equation for VG, 0.100 omega. Then B over 2 is 0.100. So simplifying the equation, the left hand side would be equal to 3.24, and then right hand side 0.15 omega. So omega is equal to 3.24 divided by 0.15. So this is equal to 21.6 radians per second. So we need G. So for letter A, this problem, so VG, we will use the equation for VG. So VG is 0.1 times omega, so that's 0.1 times 21.6 radians per second. So this is equal to 2.16 meters per second. So that's our answer for letter A. Now for letter B, what we need to solve is the impulsive reaction, so the force at point A if the bullet becomes embedded for or in 2 milliseconds. So we're looking for F here. So kindly refer to our sketch to see what where F is here. So to solve for this, we will apply the impulse momentum theorem, which states that the change in momentum is equal to the impulse. So take note that that the impulsive reaction force here is two-dimensional, so as what you can see in the diagram. So we'll have two equations, so one for each axis. So let's start first with along x. So along x, our equation would be, the mass of the panel times Bg minus the mass of the bullet times VO cosine 30 degrees, because we're just after the horizontal component. So equal to f sub x times delta t. So this is the equation for impulse. So we can now solve for f sub x. So substituting the values, f sub x will be equal to, so f sub x would be equal to this entire left-hand side divided by the time interval. So that would be 9 kilograms times 2.16 meters per second minus the mass of the bullet 0.045 kilogram times 400 meters per second cosine 30 degrees. Then all over the time interval, which is 2 milliseconds. So that's 2 times 10 raised to negative 3 seconds. So this will give us a value of 1926 newtons. So this is for the x component of the force. Now, for the y component, so along y, our equation would be only mb vo sine 30 degrees equals f sub y times the time interval. So, substituting the values, f sub y will be equal to the left-hand side over the time interval. So, f sub y equals, so 0.0450 kilogram times 400 times sine 30 meters per second times sine 30 all over, again, 2 milliseconds. So that's 2 times 10 raised to negative 3 seconds. So, f sub y is equal to 4,500 newtons. So, now that we have the components, we can now calculate for the resultant force. So, or the force F. So, for the magnitude, so we'll use Pythagorean theorem. So, F equals the square root of the x component and plus the square of the y component. So, 1926 newtons squared plus 4,500 newtons squared. Then, square root, get the square root. So, this is equal to 4895 newtons. Then, for the angle, so that would be theta equals arctangent of y over x, so that the angle would be with respect to the positive x-axis. So 4,500 newtons over 1926 newtons. Okay, so this is equal to 66.8 degrees. So, hence, the impulsive reaction force is equal to 4,895 newtons, 66.8 degrees from the x-axis or north of east.